Yeah.
Okay, thanks, Renji, and thank you, Renji and Nicola, for this great opportunity to give this course. I gave a few versions of this course in the past. This one is an updated one since I haven't been giving it for a few years. So there's new things, a lot of new things, but I try not to spoil things that came out this year and the talks wasn't given yet, either for my stuff or for other stuff. So without further ado, let's begin. Okay, first of all, what are we talking about when we're talking about directional fields? Basically, we have some kind of domain omega and a geometric domain, and in each such point P in this domain, we have a collection of vectors, and the degree of the field n is how many vectors we have at this point. So let's look at a few of the variants that are possible. Okay, so the most classical variant is like a 2D image, which might be a spherical image in this case, for instance, the Earth, where the field is a single field, n equals 1, a single vector field, like, for instance, in this case, those are wind fields. Another variant that is very common in geometry processing is when the domain is 2D, two-manifold embedded in 3D, and the field is a tangent field. That means it's orthogonal to the normal. We'll get to it also a bit later. And one very popular field is what's called a cross field or a 4 field, where in each point there's 4 vectors that are often symmetric to each other in the shape of a cross. Another example that is becoming more popular with time in geometry processing is where the domain is actually volumetric, bounded most of the cases, and where the field is some kind of field that might be orthonormal or anything else, but it's some kind of 3D frame field that looks like a 3D cross, sometimes named octahedral. So those are very common variants. Okay, so directional fields are very basic objects in everything that involves geometry and physics. We can find them a lot in nature. For instance, in hair patterns, you can say we cannot comb a hairy boar, but we can comb a hairy human because the hair has boundaries mostly. We see it in blood flows, for instance, in this case, in the brain, in magnetism, and in fields that represent deformation, which means the way points in the field move. In this case, it's not always directional fields. And also in data analysis, where we see, for instance, traffic patterns and analyze them, and also in a way to synthesize them or control them. And consequently, in geometry processing and otherwise, everything that involves geometry, we have many applications for these things. Just to name a few, maybe a little bit more than a few. One of them, and the prominent one that uses fields that have some kind of symmetry, like cross field, is meshing, in which usually we take some kind of domain, maybe a triangle mesh, we compute a field on it, we integrate it and make it into a mesh. That's the first image here. We'll get back a little bit to that. And it's not only for a 4 symmetry that creates quad meshes, but also for 3 or 6 symmetry that can create triangle or hex meshes, as the example by Nizar et al. 2011 that you see here. And in 3D, those kind of things, for instance, can lead to hex meshes because we have a 6 symmetry in 3D. Now, meshing is not just meshing, take field, get quad mesh or otherwise. Usually, we want some kind of meshing with a special function in mind, which means we have a very special set of directional fields that will lead to this mesh. One very popular one that has already been around for a while are fields that are conjugate. And that means, and I will be more specific later, that those two fields are orthogonal according to the shape operator, like principal direction fields. And when you integrate this field, you get meshes that are planar, which are good for architecture. One other class, which is popular, are fields that are geodesic, which means when you follow their flow, they trace geodesic lines. And so you can mesh meshes in which there's no twist in the lines, and you can create them out of stripes or elastic bands. Other special functions that are used for meshing, for instance, one recent one I won't be talking about much because it's a new work to create minimal surfaces from differential fields, or another recent one to trace rulings of surfaces and by using that remesh developable surfaces. Now, we talked a little bit about 3, 6, 4 that creates a triangle and hex and quad patterns, but we often, not often actually, use alternate or unconventional symmetries. For instance, this nice stripe pattern, which has just two fields that are symmetric to each other, line fields that create stripe patterns, or any other arbitrary pattern that can create, for instance, Penrose patterns on surfaces where it equals 5 or bigger than 7 and other variants. Other applications that are not specifically meshing are taking some illustrations which you can refer to as, like, in a way, sparse field, because you have some directional constraints, soft or hard, on some kind of image or the surface, and you can interpolate them to create actual shapes or vectorial contours from those initial things. They usually use fields that get interpolated from these initial constraints to generate the final shape or image. And of course, fields naturally appear and therefore simulated like this in many applications. Two noted ones that I put here, one of them is climate simulation, where we talk about wind or precipitation, or for instance, in this case, this is Greenland, an ice melting sheet and its patterns of melting. Or this paper about fluid simulation that uses Clebsch maps. Of course, vector fields appear in other applications that use them as features or as features in objects. For instance, when we want to learn the alignment of contours from objects, in this case, some kind of polygonal building extraction, or we want to learn surface features by looking at the surrounding of a point and the vector field on that surrounding, and learn features this way. Okay, so this was already a plethora of application, but not exhaustive. And now let's get a little bit into the formalities of what happens in the continuum with fields and what happens in the discrete right after. So in fields of surfaces, we have this in its surface. This is our domain omega from before, where a vector field or a one vector field is a single vector field per point. Here you can see it. This is actually discrete, but you can think about like as a sampling of a continuous vector field on the surface, where you can look at it, you can already see some trend. You can see symmetry between those four wings of this object. You can definitely see a vortex in the middle, which also marked as red as a singularity, and you can see trend. So your eyes can follow the field to see the flow lines that you can integrate manually or visually. And then the variants are rotationally symmetric fields, where in each point we have, it's like a single vector field, but we don't care about the specific direction, not like a wind field which flows from source to target, but we can think about all this direction. So it's kind of a line field, a two rotational symmetry, a rosy field, or into the right, you can see a cross field, a four rosy field, which has four different directions at each point, exactly the same way a quad mesh would have four different directions at each quad. And they don't have to be symmetric. It can be any directional fields. At each point, you can have arbitrary vectors with arbitrary symmetry, like in this case. Okay, let's do a little bit of formalities in the continuous case. I tried really hard not to make it difficult and intuitive, because this is something that can get bad really easily when you follow the rabbit hole differential geometry. So I hope it's fine. So a tangent and directional field is actually a map between what's called the tangent bundle, which means the set of all tangent spaces in every point, basically. Everything you can put a vector on. And this is actually a map to Rn times 3, which means because it's in 3D specifically, then each vector in each point can be parameterized in a raw way by an x, y, z, and then you have n vectors per point, which means a single directional object. Okay? And we usually, and I will mostly in this work, in this talk about this, assume the fields are tangent. That means they're orthogonal to the normal, and we don't actually have 3 degrees of freedom, although we might represent it this way. We only have 2 degrees of freedom, since the normal degree of freedom doesn't exist. Now, since we want to parameterize it in a nicer way that gets rid of the redundant degree of freedom, then we usually admit basis vectors, which are also fields on a surface, okay, B1 and B2 tangent fields per point. Okay, and when we use those degrees of freedom, the field can be represented in the compressed way, let's call it, in Cartesian coordinate xy, okay, where this xy is locally according to the basis. And the basis is defined per point, which means the xy in one tangent plane and the xy in another tangent plane, even if it's close by, can be totally unrelated in general, unless you know the basis, and that's something we'll touch very soon. Alternative to these Cartesian representations, which are in a way equivalent, one of them is perfectly equivalent, and that's a complex representation, simply having b1 plus ib2 as the basis, and using xy this way as a single complex number instead of two numbers in R2. That's totally equivalent. But we can also have a polar representation where we just use the polar coordinates of the point, but this has a few caveats that we will touch further on. And now I told you the basis itself is a vector field, and those number xy become compressed, which means they depend on this parameterization, which is totally arbitrary. So how do we know when two vectors that are nearby are similar, or how do we compare between them? How do we do a derivative? All those questions are equivalent. Let's see how we do that. So how do we differentiate, compare a vector in 2 points on the surface with 2 different tangent planes? We need to take into account the change of basis. So the derivative between the xy of the one and the xy of the other needs to just account for the derivative of the basis itself. And this thing is called a covariant derivative. Like a derivative, it has to assume some affine metric. I won't go into what does it mean of it being affine. Just go into the raw understanding of what a covariant derivative is, basically. So you want to derive along some kind of vector w, which is infinitesimal in this case. There's a limit. So between a point p and p plus some epsilon going to 0 times the w, in this case. And there's 2 components to this derivative to make the intrinsic comparison mean anything. First of all is the usual derivative of coordinates, which means literally the derivative of the xy as they change. But then you need to account of what's the meaning of xy and how the meaning itself of xy in the basis changes. This is the first one. And then we're looking at the change in the basis, which means the derivative of the basis, and since the basis is always orthogonal at unit length, it's a kind of a basis angular velocity, the way the basis changes along this line. This is the matrix J. Okay, so this is nothing but derivation in parts in some kind of way, if you think about it. But basically, you have a derivative of the coordinates and a derivative of the basis. If for some reason you could somehow flatten the basis, which happens in the discrete set, and rotate one basis to have another, it's a literal just derivative of the coordinates, nothing more, which makes sense, and this is what we do in the plane. Okay, since we have a way to compare between vectors and differentiate between them, we can ask ourselves a question: what happens if the derivative is actually 0? So what happens if we take a vector and we move it along a path in a way that preserves its parallelity according to this derivative? Okay, so this is parallel transfer. We can do that. Look at the left image. We can just fly around the vector as we want. What happens if we close the path? So if we close the path, it so happens to be that your vector that you flew across the surrounding does not return to the same original vector. And this phenomenon of not returning to the same original vector is called holonomy, okay, where the transport is non-trivial and the culprit is Gaussian curvature. Okay? This also happens in the discrete, as we are going to see. More formally, if the path is simply connected, then the amount of angles you gather, okay, along a path that you can have some kind of meaningful inside to it that you capture along this path, is the total integrated Gaussian curvature of this path. Okay? Modulo 2 pi, and that's also very important. And that also brings the question, how do I choose which side of the path? It doesn't matter, by the way. It will always assign, but never mind that. Holonomy is always modulus 2 pi, although the vector field could have rotated a lot along that path. That's the definition. Okay, so now we can also talk about related stuff. For instance, one of them are singularities. Consider you already have a vector field. It's not necessarily parallel. That means that when you go from one point to another, there's some kind of covariant derivative that is not 0, but the field already exists. So you go from one vector to the other, 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 and then you will return to the original one because you're just walking on the vector and gathering rotations. But it's not always the case that you just have one rotated one way and then the other. You could also do full rotations, like going around the sun, for instance. And the amount of full rotations that you do is the index of the field. For instance, you can see in this image, some of them you go one way and some of them you go the other. And the amount of indices that you can do is not, first of all, it's always integer by design because you return from one vector to the other, so it's always integer. The second thing, that it doesn't distinguish between source single vortices. In the terms of index, all of them are just rotated versions of the other. Take a source like the sun, rotate everything, it's a vortex, you still have the same index. And the sum of indices, according to the Poincaré theorem, I'm missing the graph, the sum of indices exactly reproduces the Euler characteristic of the surface. And that means that for a specific Euler characteristic, you will have a specific sum of singularities. And for instance, for closed surfaces that don't have genus zero, you must have singularities in the field, the Heritable Theorem. And this also brings another view of a vector field. I'm saying, okay, you walk from one vector field to the other. There's going to be some rotation because the field already exists. Then you can think about it in kind of a dual way. And I'm saying, okay, the vector fields are not parallel in some sense. For instance, like the one I gave you that is also called Levi-Civita connection. But the vector field defines what's parallel. That means moving between this vector and the other vector is now the new parallel. So it defines a new metric which is flat, actually, because you always return to the same vector after each rotation, except there are cone points. And cone points are the places where you have an index that is non-trivial. Okay, this was a single vector field, but I promised you to also talk about n field singularities. What happens there? In fact, surprisingly, not that much. Is very similar. So you walk around the vector field from one point to the other, as you can see in all those tweet images. But instead of returning to the same vector, if after a rotation, after a back rotation, or just like this, you return to another vector, like click one to the right or click one to the left in the cross field. So it's the same definition, except the index is not integral. So you don't rotate a full rotation or a minus full rotation. You can have multiples of 1 over n. For instance, from left to right here, it's a full rotation of half, a quarter, 0, it's nothing, and minus a quarter and minus half. You can always look about it if you cut those black lines and you unfold them, that then you have a positive index if you're missing something, like the amount of quartiles you're missing is the positive 1 divided by index. And if you're adding a quartile, you're owing an index, so your index is negative. Okay. Another viewpoint that I will pursue a little bit less, but you need it for completeness, is the covector, another representation of something that is equivalent to some aspect, where instead of representing vector fields, abstractly represent linear functionals. That means some kind of function that it's a vector field and a vector at each point and produces a scalar function. That's the entire definition you need of something that is a one-form, a covector, taking vectors into scalar. But if you insist to put it in coordinates, it will have two components, this eta x and eta y. Okay, what does it have to do with us? In the case you already have a metric, okay, then those linear functions are dual to vectors, can be implemented by vectors eta x and eta y. So this map can be simply implemented as some kind of dot product, which means it's like a directional derivative to some extent, although the original definition does not need it to be a directional derivative. It's just a linear functional. But if you have a vector, then any vector can be dualized to be this linear functional by the operation of the dot product. So given a vector as input and your eta vector, you just dot product between them, and that's your linear function. So this is also a representation of vectors, and it's dualized, so those are covectors. One interesting point is that in case there is an input which is a function, not a vector, then you can say something, okay, let's take this function, let's derive it, take the differential, okay, or the gradient in this case, and then dot product with a vector. So you have a map between a scalar and a scalar, which is a functional map to some extent. And this map also encodes this kind of vector field V. And that is also the viewpoint of several of our methods. Those things are totally equivalent in the continuous setting, but not in the discrete setting. Okay, so it identifies a field with an operator on functions, taking a function f to sum the result of eta f. Okay, so this was the continuum. I hope it wasn't a lot. It was maybe barely enough to understand what's going on in the latter part. And then let's talk about how to do it in the discrete setting. So what are the challenges in the discrete setting? The usual challenge in everything discretized is that things become discontinuous. So the tangent spaces are usually a discontinuous set of tangent plane where you have vectors on this one and vectors on that one. They have some kind of finite difference between them in some kind of measure, and they're not continuous. But in fields, there are several other difficulties that rise from the nature of directional fields. So first of all, there's the problem of connection. How do I compare two discrete tangent spaces that are somehow far apart? In n-directional field, there's also the unique problem of matching, because when you have several fields in the continuum that flow to each other, every individual vector flows to every other individual vector. But here, sometimes you have the problem where you have some kind of cross field here, a cross field there. Which vector goes to which other vector? How do I compare them exactly, if I even need to? And then even if you can match between them, there's still the problem of interpolation. What happened in the middle? It's also not an obvious thing. So one could say, okay, let's consider like the shortest rotation between one and the other, as if in the middle there was this progression, or we can consider that there was a lot of rotation between them. Now you can be smart and say, okay, always assume shortest rotation, but this is actually, as we will see in the subring thing, not always the correct representation in a way. Sometimes you need to explicitly encode big rotations even if you don't see them. So let's see how works dealt with those issues. Okay, so let's first talk about the discrete connection, which is actually the easy part, the most understandable. Suppose we have two tangent planes, still abstract. I'm not talking about specific discretization, vertex, edge, or face. That's a bit later. Then we need some kind of bijective linear map between the adjacent tangent spaces, or in more simple words, say which two vectors are the same or parallel in this sense, so we can derive between them. Two popular choices that are actually pretty much equivalent is one of them is flattening. So can somehow transform the two spaces into a single space where you can co-parameterize them, have a single axis system, and just compare like this, and then use the map A to C to B as the connection. And alternatively, what we actually use in practice, is have some kind of agreed upon vector that is mutual between them, and then just align the basis to this vector as if it's the new x-axis. This is totally the same, actually. Okay, so in case of rotations, we want to ask ourselves what happens in between. Okay, then valid rotation choices are indeed, in this case, either this 45-degree pi/4 rotation, or any other rotation, but there's not just arbitrary rotation, because we always go from the blue field to the red field, and therefore all rotation can be parameterized by some integer k in this case, such that we have a principal rotation, which is the difference between being actually totally parallel, and what's called a period jump between the vectors. So this parameters the entire set of valid rotation choices if we have the blue and the red fields. In case the fields are given as implicit or in Cartesian, then we don't have this information of the period jump, and I will also get back to it really soon. We can only assume there was a principal rotation between them, and it also produces some problems. In case we are explicitly having this angle delta that you see here, then we usually also encode the period jump, which means we give the explicit rotation, we don't have this problem. Okay, but this was for a single vector field. What do we do with matching? So suppose we were blindly given this U1, U2, U3, V1, V2, V3 on two faces F and G respectively. How do we know their current coloring? How do we know to match between them? Well, there is something that is kind of visually and mathematically obvious. Also, in this case, you know which vector goes to which other vector, and another choice does not seem logical, where the choice is kind of, let's call it the least action choice. First of all, we reduce the problem to order preserving. So if we match this U1 to U1, then this is parameterizes the entire choice. U2 has to go to V2, U3 has to go to V3, and so forth. And so it gives us n possible choices because we can move one to the other and click them to get all the choices. Which is best to choose, or the least action one to choose. Okay, so this one will look too obvious, but we can also do another one. Yes, that's a choice. So to do that, let's talk about how to even measure the price of a choice. So we look at two of them after we did the connection between them. So now they're represented in the same basis. And then we look at the effort of the choice. How much rotation do we have to do to get from one to the other? Okay, that's what we call the effort. And now what we notice is that to take the other choice, if we maintain the signs between how much we're rotating to each other, then we pay with a sum of extra 2 pi, because it's like paying with the sum of the rotation and then another full click between all vectors if we keep the order preservation. So if we have all the order preserving matchings, they all differ by 2 pi. And that means we already have the answer of what is the least action. Okay, the one that is between minus pi and pi, aka the principal matching. And there's always going to be one. By the way, if the fields are perfectly symmetric, that's also the closest rotation matching that we use for cross fields. Exactly the one. Okay. And this also gives us a discrete definition of singularities, which mirrors the structure of the one we gave in the continuum. Okay, we go around the cycle after we had computed the matching. And then, oops, we suddenly return to a vector we haven't began with. Okay, so we see how many clicks we made. In this case, there's a -1 click because we went one to the left. So the entire summed matching has an index of singularity that is how many clicks we went left or right, and that's a sign, divided by the order of the field. Okay, and the induced curvature, if this is our new metric, the amount of rotation is 2 pi divided by k. Of course, this totally reproduces the sum of indices, so this is structure preserving. I hope I'm not running too fast because this is a problem of doing a summer school without seeing faces of people in disbelief. So, but you have a YouTube video of this, you can rewatch it if you'd like. So I'm going to address actually a problem of implicit fields. I made implicit fields sound a little bit too good. I'm saying, why bother with this case number? Let's just assume all rotations are the smallest rotations, and we don't bother with actually doing those nasty integer. We're assuming everything is implicit. But that is a problem. That means if you have a low valence cycle, like for instance, you have only one ring, which is degree 5, then if you always assume the shortest rotation, you can include so much rotation in it. So you cannot really represent higher order singularities. So for instance, if you take this image and you try to force a higher order singularity around it, and you try to find out automatically by principal matching what the singularity is, you're instead going to get a bunch of lower order singularities, which are called singularity party. It's a very known artifact in matching, and I'm going to demonstrate it right now. Oops, spoilers. New share. So I hope you're all seeing this. So first, I explicitly force a singularity of higher order. This is relatively low order. Now I'm going to increase the index, increase. Before that, you've seen the index going around a lot of rotations. And basically what you're seeing right now is discretely is noise. So I force so much rotation between every 2 triangles that if I try to reproduce it implicitly, like now I forget about the index I gave, and I'm trying to say, please try to figure out the index by principal matching, and I'm getting this. So this is what the computer thinks. This is the index of everything that's happening here. It's total noise. And I will keep increasing the index, okay? And you'll see this nice disco, even if I go the other way around. So I'm going to try to force a very high, this is a very low one, so it found the index, but I'm going to try to force a very high positive index, okay? And when this is the result of principal matching, it looks like noise. So this is an actual problem when your mesh is, your valences are too coarse for high order singularities. Okay, let's switch back. All right, good. So let's talk a little bit more about possible choices of discretization. So discontinuity in the abstract sense is not the only problem. We have to decide where quantities lived, or in a little bit more formalities, what is our function space, discrete function space that we are using. There's usually three canonical choices that can be intermixed: vertex-based fields, edge-based fields that have several flavors, and face-based fields. And let's briefly go through all the implications of those choices. Okay, so face-based fields, okay, they are in a way like the most natural, obvious choice in a way, because every face has a normal, has a tangent space. It's very natural to define fields on that space, which are usually piecewise constant, although not necessarily. And how do you do the connection? There's always a mutual edge on the flap between two triangles, and you're just saying, okay, I'm canceling out, considering the difference in the representation of the edge on one side, the half edge, and the edge of the other. So that's how I'm flattening the basis on the flap, and I'm able to compute differences between two neighboring triangles. Except this is extremely discontinuous at edges and at vertices. The continuity here is really bad. But you do have structure preservation. I will be a little bit more formal what it means later. In which you have a Hodge decomposition which is unique and always existing. That means a field in every face can always be decomposed into the gradient of a function on vertices. So we have v minus 1 degrees of freedom because there's a translation one. And the field is always 2v, plus the rotated gradient from a non-conforming edge function, which is e minus 1 consecutively. And then when you add up those things to the Euler characteristic, you get that the space of harmonic functions is exactly the correct ones. So you can always do Hodge decompositions, which are structure preserving. Vertex-based fields are actually kind of similar to face-based fields in the approach, except they're kind of dual in the way they do things. But there's similar properties between them. Let's a little bit review those. Usually the common flavor, which is also exists in face-based fields, is that you parameterize the vertex tangent space, or in some way the exponential map. That means you take a vertex in the one ring, and you give a parameterization according to the angle around it, some kind of polar parameterization of where you put the field. So the field itself can appear in any one of those triangles of those vertices, and the parameterization is according to some angle beginning from some arbitrary, which defines the basis. So this effectively kind of uses a geodesic polar map, and it pushes the curvature inside faces. I won't go into each math. You can look at the details on those papers. How do you do connection? In exactly the same way. So you have two bases, and you have a mutual vector between them, which is exactly a mutual edge between two neighboring tangent spaces. Other ways are to actually explicitly parameterize piecewise linear charts. This happens to the work to the right, Leo et al. 2016. So these are nice representation, and they are usually advantages to face-based ones because they have more continuity and they allow for second-order pointwise operators. But they're, well, as much as I know, and so far this is future work, not structure preserving. So there's no clear function space that you can break them into gradient, cogradient, and harmonic fields. And then there's edge-based fields, and I'll talk about two main approaches. One of them, it's a very popular one, it's actually even more ancient to the face-based one in a way, are differential forms, where instead of encoding the actual pointwise field, we encode its integration on an edge, which is basically a single number per oriented edge, and this is the differential that the field induces on the edge. Like if you had thought about the edge as a single entity, and you integrated the field upon it, it's actually target minus source, if you think about it this way. And this is, by definition, a structure-preserving representation in which you have clear differential and co-differential operators that they have an exact structure, so d squared equals 0 and co-d squared equals 0, and that means there's also a perfectly structure-preserving Hodge decomposition. In fact, harmonic differential forms are totally isomorphic to face-based harmonic forms, but I won't go into it. Another flavor, actually a more recent one of edge-based field, is one that says that we are going to use them as some kind of extension of non-conforming scalar functions. So we define a quantity on the mid-edge, which we interpolate linearly, but in a non-conforming way, which doesn't agree between two flaps on anything but the mid-edge point. But what we gain by losing the continuity between flaps is that we have a field which is piecewise linear instead of piecewise constant. So it can have a lot of properties inside triangles that we don't have in piecewise constant field, for instance, pointwise divergence and curve. Usually the field is encoded by breaking into parts that are orthogonal to the edge and parallel to the edge, which allows us to separate it to extrinsic and intrinsic parts. One thing that can mitigate problems that happens on coarse meshes, for instance, those singularity parties, are using fields on subdivision surfaces, where we have a field in such a way on a coarse mesh that we can subdivide and get a field on a fine mesh. Of course, you can always subdivide something in some kind of linear way, but the point is to do it in a way that preserves some kind of properties. So you can enjoy degrees of freedom that are coarse, okay, but have something that is actually fine, which is also akin to working with basis functions that are like spline functions or subdivision basis functions that have higher continuity. This overcomes to some extent the sampling issue. And usually, the point of those two papers, one on subdividing differential forms and one recent mine on subdividing phase-space field, is to be structure preserving. And the structure those two papers chose was that fields that are gradient fields, which means they can integrate into a function in the coarse mesh, they subdivide into fields that can be integrated into a gradient also in the fine mesh. And if the field has some kind of curl, then it subdivides into fine curl where the subdivision of the curl itself is also smooth. So that allows also for the Hodge decomposition to carry through. All right, so this was about discretization. Let's talk a little bit about representation. I will repeat a little bit of stuff, but in different contexts, so it's more clear what this is supposed to mean in this case. Let's talk first about a single vector field, okay, a single one directional. So in a Cartesian representation, again, we can either do it raw or dependent on a local basis. Okay. Alternatively and equivalently, almost, at least in a single tangent space, we can do it in a polar representation. All right. Now, next, what happens if we want to have a unit field, for instance? Well, the implicit one doesn't encode it directly. We need to have some kind of constraint. But in the polar one, we just kill the R in this case. Okay, great. Let's use polar fields. Except, now we have a model problem. What if we want to compare two vectors? Let's say they are parallel. We use the connection. I factored it out. In the implicit step, we just say if they're both equal after this factoring out of the connection, perfect, they're equal. But in the polar setting, something weird happens. The angle is not unique because you can have an angle of 45 degrees or 405 degrees. They will look the same, but they're not the same. But maybe I want them not to be the same. Okay, so let's look at the example. I went through a rotation in some abstract tangent spaces. And then I have reached the same vector, except I didn't reach the same vector. I have a singularity in the middle. And this gets encoded in this. And when I would only compare those two vectors in the implicit setting, I wouldn't see the difference. And that's exactly why implicit setting does not see the singularity unless you do explicit matching to recover this angle. It could be this one. It depends where I started my zero. Okay, so the 2 pi invariance is built in Cartesian representation, implicit representation, but not in polar. So in polar, you can either just assume it's modulo 2 pi and you kind of Cartesianize the polar, and we got the same problems. Or you can explicitly model those period jumps. You can minimize on it or not minimize on it, or just encode it, okay, in this case. And then you have an explicit choice of the period. And then you have control over the topology of the field, which is very simple in fields that use angles. Okay, so for instance, you can dictate those things. If you dictate everyone to be 60, then you're not getting a singularity here. How do you switch between them? Okay, switching between Cartesian and polar is by principal matching, like I told you before. Switching between polar and Cartesian is very simple. You just take the complex exponent. In this case, where I assume the Cartesian representation is complex, in this case, x plus iy. Okay, how do you make the difference without factoring out the connection? In a Cartesian representation, okay, I am using the connection matrix, which means there's some kind of rotation angle, big X, which is encoded with cosine and sine function that effectively kill the periods, as you see, because this is implicit in Cartesian. And this allows me to compare between them. In the angle, I still use this angle, except I also encode into it some kind of period jump, this P. So this is the transition angle, the difference of how much they are not parallel, and this is the period jump. What happens if I have n directionals? Can I just simply use multiple ones? Well, yes, but then you don't encode the structure you want to encode. Like if you just have a raw representation, no structure at all, it's fine. But if you want to impose a symmetry, then why bother doing that? You don't have those degrees of freedom. Okay, so what you can do is usually use one representative and imply the others. That can be done. Okay, so you can just follow one representative. It's a polar representation of this field. It's perfectly fine, but you can do even a little bit more. Okay, this is what happens in this case exactly. This is exactly like encoding the period jump, except divided by n in this case. In a Cartesian one, you can alternatively just multiply the angle by n, and instead of representing the fields by a single one, you represent all the fields in the same one by a vector which is sine and cosine. And if you think about it in complex coordinates, it's exactly I to the in theta, which is actually a vector in which all roots are the vectors you're looking for, the cross field. And that's why it's sometimes called a representation of the power vector of the entire cross. And this represents the cross in one go. And all the angles that when you compare between them, use this mode times n to do this. Okay, fine. So that goes for cross field. What happens if the field is not symmetric? Okay. So we have two fields. We want to compare between them. You can do the matching and compare vector-wise. That's fine. But do you want to do the matching? The matching, in a way, says, okay, I can use something polar. I can use vector to vector, but sometimes I don't want to. I want to compare them in a way that I don't need to use the matching. I don't want to know the matching because I want singularities to appear somehow naturally, like Cartesian fields. I want to compare between those two things without knowing the order or the matching. What do I do exactly? Okay. So I want to have some function that compares between them, which is invariant. That means I want to transform each one of those objects, the left one and the right one, to some representation that is comparable, that kills the order 1, 2, 3, 4. How do I do that? I'm finding some function f that does that, kills this order between the vectors. So it's symmetric by definition. Okay, so from this creature, I get a ui, and from this creature, I get a uj that I can compare between them, and they're exactly equal when the vectors are exactly equal, okay, of sub 2 parallelity, but I don't know any order of numbers of fields. So the way to do it is, in fact, if you remember, I told you about power vectors, that it's something that all its roots induce some kind of cross, or some kind of 5-field, 3-field. I took this, and instead of saying, okay, the thought process is the other way around. Instead of having some kind of number which all roots are vectors that I can compare, I'm taking all those vectors and I'm computing a polynomial such that those vectors are its roots. And that's exactly my function f. So I'm putting all those numbers as roots and collecting all those coefficients, and those coefficients are my new representation. Now, instead of using a, b, and c, or 1, 2, 3, I'm using this a plus b plus c, and this guy I'm not going to read out, and abc. Okay, and my new representation. And this is called Empori Vector. In case I have four vectors, I am using those 4. In case some of them are symmetric, like 1 and 4 are always sign symmetric and 2 and 3 are always sign symmetric, then the first one and the third one will also be 0. So you have only 2 numbers, according to the 2 degrees of freedom. So if you're using them as complex number, then it's invertible also, of course, because the fundamental theorem of algebra. So any complex polynomial has n roots. Okay. In the case where you have a general direction like the one you see in this image here, then you will get the full set of coefficients. Now, what happens with the nice subset where all of them are exactly like a perfect n rotational symmetric field? I already talked about the case where you have sign symmetry, or what happens when all of them are symmetric. Nicely enough, those things become zero. Okay, and then you only have the free coefficients, which makes sense. You have a polynomial of some z minus r times I n theta. Okay, in this case, 4, and all the roots are exactly across. So you have a linear subspace of those orthogonal cross fields. That's fun. There are many other alternatives, and it's too short of a time to talk about all of other, but most of them are very interesting and enlightening. For instance, talking about the fields as extrema of periodic circular function, which has also been revived recently as spherical harmonics in 3D by started with Ray et al. 2016 and many other works relating about it. As eigenvectors of tensors. Tensors are not exactly n-directional fields, but because they only talk about SPD matrices, but you can also represent it this way. Or again, the functional representation where instead of the field, we represent an operator in a matrix that takes one function into the other, and the field is encoded inside. This helps with a lot of applications, for instance, fluid flows and others, in a very nice structure-preserving way. Okay. Now we talked about what fields are in the continuum, a little bit about discretization, a little bit about representation. Let's talk about what we actually want to achieve with those fields. What do we want to optimize for? So objectives, or desiderata. Okay, the most common objective to almost all works is fairness. That means we want a field that is smooth, like above all others. We usually have other objectives and constraints, and we fill the gap of those things not being defined enough to have the problem with, give me the smoothest field that is also those x, y, and z. So what do we mean by smooth? We mean a field that is as parallel as possible, or sometimes written as Levi-Civita as possible if we treat the field as a connection. In angle-based approaches, it means we're gonna, after the matching, minimize the angle between them. And in Cartesian approaches, we usually compare the representative vector or the representative polyvector between two faces. Okay, how do we encode this a little bit as an energy, as parallel as possible? Basically, we want two neighboring faces to be as much the same as possible, or let's zoom out to the continuous setting. We want to minimize the Dirichlet energy on the surface, on the domain. If you write it in a variational way, sort of like as an L2 product, basically it's an L2 product, the Laplacian of the field with the field itself. Okay, so this minimizes the gradient of the field altogether. This looks scary in the continuous setting, but in fact in the discrete setting is much simpler. If you want the field to be as parallel as possible, you literally try to minimize the parallelity between two neighboring faces. So that means that you take every ij that are neighboring tangent spaces, face, vertex, whatever they may be. You're saying this vi wants to be like this vj with the appropriate connection matrix rij. And this involves some kind of metric, some kind of stiffness, something that says, what exactly am I integrating upon here? What is this d omega when I'm discretizing the energy above? Okay, and Rij is the connection matrix. So this is also like an L2 product. This discretizes exactly the same when L replaces the delta. And this L is the discrete vector Laplacian. And also there are many flavors of that one. Okay. Let's have a demo of minimizing this exact same thing on power fields. Okay, let's talk a little bit about what they do. So we have a single complex number pair constraint face that actually represents by its roots. So we give y and it represents the u. And we want to interpolate it to all the rest of the free faces. We only put it on a few boundary faces. And we minimize this Dirichlet energy. It actually looks exactly the same. This R matrix is actually just EG divided by EF. Okay, to the power of n, because we have a power of n vectors, except I just symmetrize this EF and move to the other side, but it's exactly the same energy. W is also the same energy. So basically, I'm solving a single linear system. It's because it's quadratic minimization, where the vectors I know just move to the right-hand side. After I did this, I have YF for all the faces. I'm just taking the roots of them. Okay, the choice of WE, I use this choice from Band et al. It looks like a scary choice. But actually, it's a very natural choice, and it's also, if you consider the barycentric points of every face, It's the ratio of the primal edge to the dual edge, which is exactly gives you the two-form Laplacian in coordinates. But I'm digressing. Let's move to this demo. Okay, so here is an object. The singularities are computed as principal matching. So what I'm giving is the Cartesian representation. As you can see, there's a little bit of singularity party in here. Okay, let me just try to force some faces. Okay, I'm rotating this around. You see it affects the other vectors. That's exactly what I'm computing. Okay, and if I'm trying to force more and more constraints, I'll end up with more and more singularities. This is actually surprisingly stable, but here some singularities just propped out. Okay, oh, you see, I managed to create a singularity party. Never mind. Okay. Okay, but you see the singularity. Here is a nice singularity party. See, because the field is extremely non-smooth here, also because of the geometry. Okay, because this is a very coarse mesh at this point, and the valences are not enough to encode the geometry nicely because we have a single vector per phase, and therefore we have a party here that you need to address, otherwise this won't be very nicely integrable. Okay. All right. And another demo, which is sequential. I'm doing the same, except I'm giving degrees of freedom to each individual vector. So I'm, instead of using power fields, I'm going to use the entire set of polynomial complex coefficients, which gives me, instead of a single system, it gives me a degree of freedom for the system for each coefficient. In this case, you will see it's n equals 3 and going to be free fields. Okay, but the interpolation is the same. It's just three systems. And let's go to this demo. All demos are from Directional, and in the Directional field synthesis library I gave in the Discord channel, and also here in this link, I told you which tutorial demos they are. You can play with them as much as I do now. All right, let's see this. So here are two faces. This is currently constrained. Both of them are constrained to be exactly cross fields. Okay. The video is a bit messy. And consequently, because all other coefficients are 0, then the result is 0. But let me constrain a new face. Okay, and let me choose one vector in it and move it like this. Yes. Okay. You see, I created a weird disturbance here in the middle, and this disturbance is smoothly interpolated until this nice field here, and also back here. Okay, so that's nice. If I move it again to be parallel, then it also makes out of parallels. This is because the free perfect rosy field is a linear subspace. And if I try to degenerate them very difficultly, then it will work. Okay, let's do this. So I'm getting this bird claw thing, and it interpolates nicely back to the left and right stuff. Okay. Let me just kill those demos because it's a bit taxing on my system. Okay. So I'm going to move to another demo, which is a polar demo this time. And this one is the one of index prescription. It's kind of not similar to the other because the representation is not Cartesian. What we're going to do is reproduce the trivial connection paper by Crenneto 2010. Okay, there's the original vertex curvatures, and I'm giving prescribed curvatures, which means I'm giving the rotations around every cycle. So saying where the singularities and also the generator, in this case, they're not going to be boundaries on the mesh, and the field is interpolated by finding out the differences per edge and then reproducing the field. Okay, so I'm minimizing the polar Dirichlet energy, which means the rotation angles between every two neighboring tangent spaces. Under the linear constraints, that the sum of those angles reproduces a specific cone. Let's look at this demo. Okay, this is the original one. Okay, in the fertility mesh, you see those singularities that I prescribed. They're not device from principal matching, they are prescribed. Let me, for instance, now do something weird. I'm gonna put a new singularity. Oops, something bad happened. It's not exactly the same. Those fields are somehow not normal, and you see there's weird stuff going on here. Some singularity would have popped up. What happened? What happened is that I put a new index and I didn't pay for it because the sum of indices has to sum up exactly to 2 pi chi. Well, the sum of indices is chi, but and every time I introduce a new point index, I have to pay with it with another. So I will introduce a new one and pay with it with a minus index, and voila, it's good again. Okay, so you can look. Let me play with it a little bit more. That it will look. I will increase the index by a lot. Okay, and I will increase this index by a lot. This is very fun to play with, by the way. Yes. So I don't know how much index. I actually have. I think each one of them is a 6. Yes. So when you zoom out, you can see the effect of this index. Okay, because this mesh is somewhat high enough, but inside there's a lot of rotation, and it's like wow noise. So I don't have this in this demo, but if you try to do the principal matching, which means avoid not to know the rotations and try to devise them with a Cartesian representation, you would get that there's a singularity part in here. Okay. Another thing I can do here is change the index of generators, because generators are independent indices when I have a genus. So you see here, this one is kind of straight. Well, not really defined this way because every generator also has geodesic curvature. Let me increase its index and see what's happening. Every choice is valid in a generator. Generators don't add to the general index. Why? This actually took me a long time to figure out. An intuitive answer is that generators are actually 2 boundary loops minusing each other. In a way, you can cut them and do it the same way, and then the index on every boundary with this boundary loop and this boundary loop exactly minus each other. So generators, you see, I created a lot of generator-like rotation here, but it's valid, right? You can also take those 2 singularities. This add a plus, oops, maybe add a minus, and this kill altogether. Yes. All right, that's great. Right, I think that's it with the demos for now. There's many more demos in Directional of nice stuff, but some of them also are heavy computational, so they take more computation to do. Okay. Right, let's move on. In case I don't know the original topology, which was actually one of the more classical problems in cross fields, okay, and I use an angle-based representation, then I have to explicitly have this row as a variable, an index matching that I optimize on. Okay, that becomes a mixed integer optimization, which also exists in several works. This is still used because you sometimes do want the angles, but because of the high computational effort, this approach is approached carefully. Yes, to do that because it also has a lot of local minima. There are some newer stuff to do this kind of model this kind of behavior. Some of them do Gauss ideal iterations, like this Jacob et al., and several others. Okay, so this was the smoothness one. Let's talk about other objectives that are important. One other objective that is a little bit complementary to smoothness is orthogonality. Now I'm saying orthogonality, but actually it's in a way kind of a simple object symmetry. So in the case where you have a cross field, you usually want the cross field to be as orthogonal as you dare, as power field as possible. Okay, so if it's, for instance, a Empori vector, you want all non-free coefficients to be as 0 as possible, because you want the field to be nice, not to be degenerate such that 2 vectors are very close to each other. Okay, because that usually creates bad elements in the mesh. If it's 4, then it's orthogonal. If it's 5, then you want it to be like a 5-star as much as possible. Other objectives are, for instance, controlling the singularities themselves in several ways, maybe change and not only use Dirichlet energy, like in this example, use some kind of mixture of conformal energy. Maybe you want the field as a flow to induce isometry, for instance, find out how the mesh is isometric or the formation is isometric in this case. So you want the field to flow those infinitesimal isometries. In this case, it's called a killing field, for instance, one that flows this kind of field. So you want to compute a field which is as killing as possible, or deform a mesh to have those kind of fields. And now let's talk a little bit about the complementary to objectives, which can sometimes be also used softly, and those are constraints, what we want the field to hold exactly. And this, of course, depends on the function. So one very important constraint is also we all use alongside smoothness is alignment. There are almost always elements in a mesh such that a user gave some kind of stroke on or sharp features that we want the field to align to. And in this case, if you have a single vector field or line field, then maybe the alignment is simple, just saying the vector at this point has to be equal to that field. That's what I did in those demos. But sometimes you only want to have a partial way to align. For instance, in some kind of polyvector field, you want only one of the vectors to be something, and the rest of them are free to do whatever they want. Of course, be as smooth and orthogonal as possible. So the user or a sharp feature give only a few strokes, and you want to get the entire field. So that's a constraint, and most methods allow that even to a partial extent. Okay, and of course, a constraint I talked about a lot is topology, to be able to specifically put points of singularities and be able to get a field with a specific topology. So those are the works that do that. Usually, but not always, they control angle-based or polar representations, because in those you can do that explicitly and oftentimes linearly. One very popular constraint, especially in industrial design and architectural geometry, is conjugacy. Conjugacy is something I referred to before, and now will be a little bit more formal. Two vector fields, tangent vector fields, are conjugate, given the second fundamental operator, if they are orthogonal according to this operator. Basically, what it means is that infinitesimally, if you trace those two vectors and back again, they form an infinitesimal planar quad. They don't have a twist in the curvature. Principal direction fields are the model example of fields that are conjugate, because they are both orthogonal through the shape operator with this norm and with the usual metric on the surface. Why do we want it? Because if we have some kind of parameterization where the infinitesimal quads don't have a twist, then what we expect is to mesh this parameterization with quads that are finite, but that are very close to being planar. So very small and non-deforming optimization will make us a planar quad mesh, which is something we want for architecture and design, because we can fit flat pieces of glass or metal or anything on it. So in this case, for quad meshes, and in newer work, which I will not divulge much detail on, that's fine, for hex meshes. And in the case of hex meshes, also the shape changes, but they're also planar. Hex is in hexagonal, not hexahedron, which I also talked about before. One other constraint is symmetry, and in this case, not a symmetry of a single object, so it's as n-rosy as possible, but a global symmetry on the mesh. So oftentimes when we want to do flows or even more importantly, mesh, and the object has some kind of symmetry, we expect that the symmetry will be induced in the vector field itself, in the directional field itself, and thus in the mesh. So this is also a constraint that we want to say to the mesh, here between the left and the right, there is some kind of symmetry, and make the mesh exactly as symmetric and the field exactly as symmetric on both sides. Another very nice constraint that is actually very useful is foliation. And what does it mean? We want to compute a field, and that's a recent work by Campanella 2017, such that when we trace the lines on those fields, they foliate the surface. So those lines don't go into each other, they don't intersect. There is a clear function between those noodles, the foliation lines, which is, there is a clear function in the way, and I won't go into the formalities here, it's a little bit annoying, such that every point in the domain you're foliating belongs to exactly one of those foliations. Okay, so it breaks up the space, that's exactly the definition of foliation. And you also can use the dual one, so you can break a volumetric piece into many of those kind of, well, they're not exactly level sets, but surfaces that don't intersect each other. Okay, so that's a very useful way to break up a volumetric domain. And the way they use it is they computed the directional field that has those properties that when you integrate along its flows, it creates a foliation. Another constraint that I talked about a lot, and then let's see what it's a little bit more made of, is structure preservation. And I promised you that this kind of thing also promises a Hodge composition. Let's see a little bit why. In the continuous setting, if a vector field is the gradient of some function, then it means the vector field is curve-free. That's called an exact structure. And if the vector field is the either, let's call it the co-gradient or the curl of some other field, some kind of vector potential, then the divergence of this vector field is also 0. And that is something we expect many vector fields methods and the differential operators to hold. Okay, and Verdetsky 2006 and also other methods showed that this is only possible by mixing conforming elements and non-conforming elements. Specifically, what the popular thing is to have the functions that we take the gradient of on the vertices, and the function, if we are talking phase-based fields, and the functions that is non-conforming on the edges as a non-conforming functions. And this preservation of structure allows for the existence and uniqueness of the Hodge decomposition, which means if you have a field, it breaks about to those F and G and harmonic components H, which are unique, existing, and also have the correct dimensionality. So there's no 2F that have the same one. I should also note that this also exists in differential form. The meaning of this cross of gradient is exactly d square, and the meaning of this divergence of a curve is exactly the co-d square. Well, they are equivalent, let's call it this way. And in differential form, it works with vertex-based function and phase-based function instead of conforming ones. Phase-based two forms. Okay, another constraint I want to talk a little bit more on. Actually, I'm very good in timing for some reason. I must be in a lot of hurry because I'm usually late. Okay, so sorry for that, but I think you also have a YouTube that you can watch in another speed. So one constraint is integrability. One big application that I talk about of fields is that we want to integrate those fields into parameterization and use them as meshes. So usually when you do want to do that, you don't want to induce any error. You want a field to serve as candidate gradients, and you want the integration to have as little error as possible. So a necessary condition, this is much like Hodge decomposition, you want to find a function f such that the v that you have is the gradient of, and necessary condition is to be curve-free. And necessary but not sufficient. So some works computed that. So if you have some kind of strokes, this is specifically Diamante 2015, which optimized on Empori vectors. They computed the field which is non-orthogonal but curve-free. So the parameterization is what you see is what you get. If you don't force it to be integer, it's exactly zero error integration from the field to the parameterization. So let's see exactly what happened. In more classical method, for instance, if you use a cross field and you just integrate it, so you do field to parameterization, doing integration. So if it's not integrable, you can get an arbitrary misalignment. If you try to force the alignment on several faces, you might get flipovers. But if you're optimizing the field to be integrable, then you get perfect alignment. So you have what you see is what you get. Okay, let's look a little bit about how integrability and discrete curve relate to each other. If you have a piecewise linear function, okay, which is represented on hat basis function, that means piecewise linear interpolated in each face. Okay, then consequently, the gradient is one piecewise constant field per face. And this field is naturally discretely curve-free because the dot product of the vectors in two faces are identified on the edge E. That's all. This minus that is also the discrete curl. And it's also related to differential form because this dot product, this nabla H dot product with E is also exactly the differential of the function on that edge E, target minus source, if you want to talk about the D of F. What happens when we have n-directional fields? We want the discrete curl on all of them. So we do indeed want of all of them. If we have two fields, how is this curve-free? It's only curve-free if there exists a matching such that by reduction, those two vectors that are matched, all of the vectors in all of those two faces are curve-free. That means an n-directional is curve-free. Now, why this direction? Why this definition? Because if you have a curve-free n-directional field, That means you're going to have a zero-error seamless parameterization, like a quad parameterization with a star. What is the star? Sorry, spoilers. The star is not including integer. So it means if you cut the mesh and integrate, and I'm going to show how in just a little bit, okay, then you're going to get exactly a zero error unless you do the integer, so before the integer. So it's a good initial solution for general meshing. Okay, let's go to other constraint, and it's a jump aside because I'm also going to return to integrability in another context. So one other constraint that will revolve back to integrability is uniform unit length. That means I want fields such that in each point, the field, all vectors have unit length. Why is it important? Because I want to integrate them into, for instance, quad meshes or nets, such that all the lengths of the edges are uniform. They are the same or equal one. It's the same up to global scale. And those kind of nets are called Chebyshev nets because they're inextensible. They're used to build grid shells, often design stands, or even, wrap fruits if that's what you're after. The thing is, when we did this Chebyshev network segment until 2019, we ran into a problem. We cannot make the directional fields we use as gradients, and here it's alpha and beta. Ignore for a moment the sharp. It means it's the sharp operator from differential forms to vector fields. Because if we need the black net that you see here, the edges, we need them to be unit length. But it does not imply that the lengths of those red vectors, the gradient we classically work with in the curve-free thing, to be unit. Only if they are exactly orthogonal. Why? Because gradients are the normals to the line. Their length encodes the difference between neighboring level sets. And if the net is not orthogonal, this distance is not the length of the edges. You have a parallelogram, and the length of those red vectors are the heights of the parallelogram, because they're the difference between two neighboring parallel lines. But I don't need the height of the parallelogram. What I need is actually the edges of the length, to constrain the lengths of the edges of the parallelogram. So instead of working with the usual gradient fields, we opted to work with the tangent field, the blue ones that you see here. Except, how do I work with integrability on tangent field? But this is actually what, if you say to a mathematician that a field is integrable, that's how they're going to think about integrability. Okay, and this integrability lies in the encoding of the Lie bracket. And basically, what does it mean? That two fields are integrable, mutually integrable, if when you follow the one and then the other infinitesimally, or when you follow the other and then the one, they end up in the same place infinitesimally. That's Lie bracket integrability. That means the commutator of this field is exactly 0. And now this even makes much sense discretely, because this literally means those two fields make an infinitesimal parallelogram. They don't break apart the parallelograms. Okay, so this is what integrability is. And now you might ask yourself, how is the curve-free one related to this one? They're equivalent in the continuum, which means if you take fields and you do this integrability, the Lie bracket integrability, and then when you dualize them, you see that the gradient fields are exactly curve-free. But this is kind of obvious in a way, because if this is integrable, there exists a parameterization. If there is a parameterization, you could just take the gradient of the parameterization, and that's going to be it. Okay, so this is the kind of integrability we use in discretize specifically. So this is coming back to another form of thinking about integrability of fields. Okay, now I will talk a little bit about how to do it in gradient fields, but it actually doesn't matter because you can convert every time to gradient fields. How do I actually do the integration? So if I have a singularity, I cannot just integrate it into a single function, because this function is going to be branched. That means if you go around some kind of singularity, you're going to not return to the original function, exactly like the field doesn't. So you're going to have to cut this mesh along a seam, and then you have to identify the field in a way that we call combing. I mean, color it in a way such that you flood field the matching, so it's trivial. So you make a blue field, a green field, and so forth, such that only on those cuts you have a matching which is non-trivial. And then you can integrate those into n different function. And if you hold the rotation constraint on this seam, okay, then you are guaranteed that the function is seamless. What does it mean, seamless? It means if you don't specifically color the functions according to colors, you're going to see that if you only draw quads of that function, that the quads match up. Now, if you only just integrate, the quads are not going to exactly match up, just their directions. If you're using integer jumps in addition, then you're going to see the quads match up, and then you can make a mesh out of it. And this is how it looks like. This is also, by the way, a demo from Directional 501. This is actually from a new package about integrability and meshing, but I'm not going to do the actual demo itself now. This is the field, as you see to the left, with the singularities. It's now combed. The field is colored. Okay, now integrated into n functions without forcing integer jumps on the seams. So you see, it looks like those are closed quads, but there's a kind of translation issue going on. And this is curve-free, so the integration here was very low error. It's not exactly curve-free, it's almost curve-free. And then I rounded up those integers, inducing a little bit of error to get from the middle one to the right one. And this one is a perfectly fully seamless parameterization. That means you can take this and create a quad mesh out of it. You can also do that for triangle meshes, hexagonal meshes, Penrose pattern, but for that you have to wait for SIGGRAPH. Okay, so this was on one leg what we kind of know how to do with fields as of yet. I want a little bit to talk about challenges in the future or challenges that are currently in work. One of the, let's call it the more biggest challenge nowadays is working with directional fields in the wild. All the algorithms I've shown before have this nice flap, there's a triangle, there's a neighboring triangle, the triangles are not degenerate, you don't have 5.5 triangles per edge or any other combination, there's no part of it point cloud, part of it missing, everything assumed really nice meshes, and even if you assumed relatively nice meshes, if they were a little bit too coarse, then it was a problem. So actually, a good direction for work into the future is directional fields in the wild. Many meshes are self-intersecting, not watertight, so that's an actual big problem that has not so far been addressed sufficiently by works on directional fields. Most existing algorithms that I showed, actually, I think all of them would fail. There's two interesting directions that are currently already implemented in several papers, but not to this specific cause exactly. One of them is, instead of representing the field on the actual mesh that you have some kind of abstract or alternative, more robust representation of the mesh using some kind of envelope, some volumetric way to represent the geometric area around this with some kind of notion of what's the direction of the surface supposed to be. Another interesting one, just from last year's SGP, is a tufted cover, which is a way to also work with meshes that are non-manifold or to complete meshes that you have got from, for instance, point cloud or stuff like this, that allowed for Laplacian operators, and also, if I remember correctly, it did allow for to work with fields that are vertex-based because of this thing. So this is a very interesting direction to work on meshes in the wild. And also level sets. So if you have something which is not the mesh, but the mesh is represented as a zero set of some sine distance function or something which is also very popular in learning nowadays, represent the field as a tangent field, but implicitly, with also the entire surrounding. And this also might be very helpful to learning of directional fields in geometry. Another challenge, and this is also something most algorithms will struggle with, except some of them, is working with big geometric data, because most of these algorithms have some kind of underlying sparse linear system. Well, the simple ones. Other ones have weird nonlinear systems, nonlinear constraints, and a lot of stuff that are a little bit nasty. But the thing that irks here is a lot of the time we want to compute solutions that are really, really smooth and not spanned by a big function space. Yes, like maybe there's some constraint here or there, but far away there's a field that is almost constant. Okay, and still you have to solve a big linear system for it. And this calls for some approach that might be multigrid. So we currently have really nice new approaches for multigrid on surfaces with simplification. This is a very new work that has not been presented yet, so I'm not going to talk about it. It's not mine. This, I think, goes in this year's SIGGRAPH. Probably the authors are also here. So, but we want methods like this that will work on directional fields. Now, I should note that in the past we had works on subdivision fields. That means we have the coarse mesh and we got the fine mesh. But we want also the other way around, to begin with big geometric data and go the other way around, coarsen it in a way that will still be structure preserving and meaningful for directional fields. Well, really good timing because I'm almost done. So there's a lot of good sources that on network, and I'm pointing some of the main ones that have code and the information about directional fields. One of them is this really great survey that preceded ours about vector field processing on triangle meshes, which is mostly on the differential part of single vector fields. It's by Fernando de Goes and others. Directional is specifically my library that has a lot of operations on direction fields, and you can also find the demos in. But there's also a lot of really good, great code that working with directional fields, especially, for instance, vertex-based one in Geometry Central, and then for differential forms in digital. And Comiso has a lot of work on seamless parametrization. And of course, a lot of those individual papers I mentioned also have code of their own to do those things. So thank you very much.
All right. Thank you, Amir, for the very nice and educational talk or lecture. And we have time for a few or a couple of questions. Please raise your hand from Zoom if you have any question. Okay, Etienne, please.
Hey, Amir.
Hi.
I had a question about the phase-based vector fields, which has been confusing me. So what's going on with the Hodge decomposition there? So like you mentioned, right? So if you have phase-based vector fields, you have 2f dimensions, and v of them are the exact one forms, right? Yeah. And then that means there's 3v left over, right? And so v does not equal 3v, right? So you have your gradient vector fields. There's v of them. You rotate them by 90 degrees. It gives you v. Co-exact one forms. Then what are the other 2v? Like, what's going on there?
Please don't ask me to do this math online. I did it many times on paper, actually, and it works. You need just the Euler characteristic, like v minus c plus f equals chi. And if you're using a triangle mesh, you also need the relation 3f equals 2e. Non-boundary, yes? That's the boundary.
Yeah, sure, no boundary. Yeah, exactly.
Yeah, sure. Yes.
Yeah.
If you use those two relations, it works out. Okay, you get exactly 2 geometric fields. And that's also what Max Verdesky showed, that you have to use non-conforming function, that the dimension of the co-gradient fields has to be e minus 1 to work. Because the original, there was one paper on direction that used v for both degrees of freedom, the gradients and the co-gradients, and then you get spurious modes for the harmonic fields.
Oh yeah, sure. This I agree with, but isn't it a problem that the dimensions don't match for the
it is, but
gradients and co-gradients?
If you use the mixed elements, that exactly works. I promise. Do the math. I can do it with you in the channel. Yes, I did it.
Okay, cool. Yeah, I'll talk to you on the Discord.
All right. Any question else? I will ask one. So we have seen you showing the demo of some of the algorithm, and it's very cool. But we miss the user interaction. It's just like magic. So anyway, is there any chance that as audience we can get access to your demo?
Yes, everything is in directional. If you in the first slide, yes, let me show it again. Okay, so let me. Where is the share screen? Yes. In the first slide, you can go to this website, and in the README, you will see a comment about SGP 2021. Yes. Can I follow it? Open link. Okay, so when I open the link, yes, then those are demos 201, 302, 303, and 401 from the tutorial. I use them as is.
Okay,
You can open the directional tutorial and play with them.
Okay, so these demos are self-explanatory or?
Yes, yes.
Yes.
They're pretty simple. You just, pick faces and choose vectors. Nothing more.
Great.
Yeah, and for those demos, this was also real time because, well, it's a simple linear system and it's also prefactored, with just different right-hand side. There are some demos in here like the seamless parameterization, the meshes, which take time because it's heavy stuff. Okay, but those ones are very simple to play with.
Okay. Okay, I don't see. I have another one. So you mentioned a couple of times about seamless parameterization. So, with this curve-free constraints, you will get, I think, I mean, in the continuous case, you can get this seamless parameterization.
Yes.
Right?
Yes.
But in practice, if you want to use it for meshing, you have this integer jump issue. And you mentioned that you can do get away with it by simply rounding.
No, you can't get away with it. What I meant is that the non-integer is a very good initial solution. Yes. And also one constraint I didn't talk about with lack of time is local injectivity. So if you have to weigh, and new papers do that, to do both curve-free and locally injective, which is order preserving, yes, then you have an initial solution, which is already a good solution and it doesn't flip. And you can use it for many other methods to round up that, tries to penalize this non-flipping. There's a lot of papers on it, but this is like a totally different subject. Yes.
Okay, so by simply rounding, you are not guaranteed to get free mesh. Okay.
You're not guaranteed at all. Yes. In a lot of meshes, it's too coarse and it's extremely sensitive. In directional, I have a way kind of better to force the local injectivity when you do that. It can fail. So this is still kind of open, how to do it, in a way that will always work. And of course, it depends on the discretization of the mesh. It can get locked, especially if you're using phase-based fields, which are very sensitive to discretization.
Right, yes. I think we have time for one more question. I will ask another one. I think it's a more general question.
I will be also around. You can ask on Discord, so don't. You can.
Yes, of course.
Think about it.
The whole lecture is about vector field on triangular meshes, to my understanding. What about like 3D fields? That's like flow fields.
Oh yes, I'm sorry for a lot of offers that are in the crowd, but there's two big subjects that I didn't even touch. One of them is 3D fields, volumetric fields, which is relatively new. I talked about only some of the initial works in passing because this you need another lecture. Yes, this is a big subject with a totally different math. Yes, there's a lot of quaternions and operators and all. There are people that can also talk about it much more than me. I only have one work on it. Yes, it's difficult. Next year SGP summer school, 3D fields.
Okay.
Yes, I forgot what was the other. I have parent brain. Maybe I remember if someone else has.
No problem.
Yes.
Yeah.
I think it was like simulation stuff. Never mind.
Typically, that's in 3D, no? I mean,
yes, in 3D, but I did touch surface-based fields. I didn't touch volumetric fields at all. Yes.
Actually, I think you mentioned one application for what's hexagonal meshing.
That's
right?
Right. That's the main application for 3D fields so far. Also, topology optimization. There are some nice works on it from recent years. Yeah, but again, a lot of material I missed. Yes.
Yeah, I'm sure it's too broad a direction of you to cover it all. Yeah. Okay. I think we are right on time. So if there's no further question from the audience for now, we will thank you again for your great talk. And please try to, if the audience have further question. Oh, actually, yes, no, that's clapping. Yeah.
I will be around this